Hi everybody, here's the quick video that I promised you for the problem we didn't really get to work totally out in class. So here's the problem, I wrote it out. A roller coaster car mass 300 kilograms starts from rest at point A. So let's draw a picture. We have a roller coaster, just like the one I drew in class. Up here at a height h is the roller coaster car. It has a mass of 300 kilograms and a velocity equals 0 at that point. We release it from rest, it slides down a hill, and realize, for example, how hard it would be to solve this hill problem because this is a hill that's curvy, doesn't even have a straight incline, so we don't even really have techniques to figure out how something would slide down this hill because, we'd have to do Newton's laws differently at every single point. It would be very complicated. Here's point B at the bottom of the hill. The roller coaster car, we're told that we want it to be moving at 30 meters per second, which sounds like a pretty fast roller coaster car. And we can assume that the entire surface of the hill is frictionless based on this problem, so there's no friction there. Then it encounters a slightly rough patch that's 25 meters long, and it has mu k equals 0.4, so we know we can calculate the frictional force, and we want to figure out at point C how fast is it going. So this is a pretty complicated problem. There's a lot going on here. We could solve this part using Newton's laws and the big three, getting the force, getting the acceleration, figuring out how far, what its velocity is at the end of that, but that would be a lot of work and a lot of physics. And then, in fact, over here, we would need calculus and the shape of the hill to be able to use Newton's laws to figure this one out. So energy is going to resolve this dilemma for us by providing a whole different way to solve this problem. So let's first look at A to B, which is what we started to do in class. And let's go to our energy transformation template equation. So we know that K at A initially plus UG at A initially, and there's no spring, so I'm leaving out elastic, plus any work done equals K at B plus UG at B. And the first thing we can say is in going from A to B, nobody touches it, and there's no friction, so there's no external forces acting on this system. There's just the ball sliding down the hill. Let's go one step further and ask now, at point A, does it have kinetic energy? Is it moving? The answer is no, it does not. It does have UG because it's at a height, and we can write that expression down, which would be mgh. And we can plug that in a second. At the end at point B, yes, it has K. It does not have any U because it has no height. And so it turns out, this tells us this is a U to K problem, and it tells us the little energy story that we had there. So 1/2 mv at B squared. Now, I gave you the math, but you'll notice it actually cancels out in this equation, so that's good because you want all the riders in the roller coaster cars to be moving at the same speed. You don't want them all moving at different speeds. That would look really weird. Everybody would be flying all over the place. So it's good that this is mass independent. So now let's put in our values. 9.8 meters per second squared times h equals 1/2, and 30 meters per second is the speed we're given, and let's square that. And I'm going to calculate it really quickly. 30 squared divided by 2 is 450, and then divide that by 9.8. I get a height of 45.9 meters, which seems about right. That seems good for a roller coaster, so that's the answer to A. H equals 45.9 meters. Okay, that's the first problem, so I did all that. Now let's look at B to C. Let me push this up here a little bit so you can still see. Let me sharpen my pencil. There we go. Always important to have a sharp pencil. Okay, B to C. So now let's look at B to C. Let's do the same thing. K at B plus UG at B plus work equals K at C plus UG at C. What I have plus work equals what I end up with. And the first thing we can notice is the problem is all happening on the ground, so there's no UG. And we know we have K at B, we know we have K at C, we know it's lost kinetic energy, so this work is going to be negative. Let's first figure out, let's put in values that we know. So for K at B, we know we're going to have 1/2 mv at B squared. Good. K at C is going to be 1/2 mv at C squared. We need to calculate this work. Let's remind ourselves over here on the side, we have to do a little bit of F equals ma. If we have Fk, mg is the weight. In this case, the normal force is mg. 300 kilograms times 9.8. Let's see. 2,940 newtons is the weight. That means the normal force is also 2,940 newtons. That tells us that Fk is mu k times 2,940, 1176 in that direction. Whoopsies, you can't see that. There you go. Okay, so let's come back to our picture. While the ball is rolling, it has the distance, the displacement is 25 meters in that direction, but the friction is about 1,176 newtons in that direction. Because the force and the distance are in opposite directions, it's going to mean that there's negative work because the force and the distance are opposite. So the work is going to be negative, let me come back over here, Fk times the distance. And that makes sense because the kinetic energy at C is less than the kinetic energy at B, meaning that there had to be a loss of energy through work which transferred into thermal energy. Let's plug in all our numbers and see how it works. 1/2 times 300 kilograms times 30 meters per second squared minus work. So 1176 newtons times 25 meters, force times distance is work, equals 1/2 times 300 kilograms times V at C squared. So let's calculate this all out. 0.5 times 300 times 30 squared is, and these numbers are going to be big, 135,000 joules of kinetic energy initially, minus 1176 times 25, 29,400 joules of negative work done by friction, which transfers into thermal energy. And that's going to give us 1/2 times 300 is 150 times V at B squared. So now let's just do this. Negative 29,000 plus 135,000 is 105,600 divided by 150 is 704. So I get 704 is V at B squared, or V at B is the square root of that, which is 26.5. So that is the final answer. Let's retrace our steps. We did the energy conservation equation. We mapped out the potential energy. We remembered that the kinetic energy here is less than the kinetic energy here. We noted the work is going to be done by friction over that distance, and it's negative because the friction acts against the distance. We plugged in our numbers for kinetic energy, work done by friction. We didn't forget the distance, or sometimes people do all this and they forget to multiply by the distance. Set it equal to the energy at C, did some arithmetic, and wound up with a velocity. And then we said, does it make sense? Yes, 26.5 is less than 30, as it should be, because negative work was done on the system. All right, I hope that was helpful. You could probably watch this on double speed if you want, so it doesn't take as long. Okay, bye.